Hello! Today's episode of FUM0024 machining. We are going to talk about the VFD programming, specifically about how to read the keyboard. In this case, keyboard is of course 3 buttons: forward, stop and reverse. Well, that's one subject, and another subject will be timers. Timers is really essential for this type of embedded programming, and therefore that's one subject of today. And last but least, okay, I have a paper there. We are going to talk about ring buffers. Well, so let's go on with, let's start with the buttons. Let me present you the 4 guys who are reading the keyboard. I am reading the key. Nobody else should be reading the key. My task is to look for the stability. Keys are switches and they don't behave well. In the switching event, they bounce on and off several times before they settle. My task is to ensure that the rest of the system gets only valid keyboard or key states. My task is to look for changes in the key state. I am storing the event. This system is based on key events. There are 2 events for each key. The key can go from off to on, that's one event, and then from on to off, that's another event. These events are stored in a buffer, which is then periodically read by the rest of the software. Key is up. This is the first time you tell me that the key is up. I'm not going to process it. Key is up. This is the second time you are telling me that the key is up. I'm not going to process it. Key is up. This is the third time you are telling me that the key is up. I'm not going to process it. Key is up. This is the 4th time you are telling me that the key is up. I am going to process that. Seems like the key is still up. No change. Key is down. This is the first time you are telling me that the key is down. I'm not going to process it. Key is down. This is the second time you are telling me that the key is down. I'm not going to process it. Key is down. This is the 4th time you are telling me that the key is down. I am going to process that. Seems like the key went down. There is a change. Since the key is now down, it is an up to down event. Key is up. This is the first time you tell me that the key is up. I'm not going to process it. Key is down. This is the first time you are telling me that the key is down. I'm not going to process it. key is up. This is the first time you tell me that the key is up. I'm not going to process it. Key is up. This is the second time you are telling me that the key is up. I'm not going to process it. Key is up. This is the third time you are telling me that the key is up. I'm not going to process it. Key is up. This is the fourth time you are telling me that the key is up. I am going to process that. Seems like the key went up. There is a change. Since the key is now up, it is an from down to up event. So, there are a few things you have to consider when designing a keyboard reader. First of all, this is very important actually. It is not a very good practice to have several points which access the hardware. Usually the system should be built in a way that it only accesses the bits or the port which is reading the keys in a single point. And after accessing the point, it should be processed immediately. And this is because if you have multiple points where you access it, you get also multiple results. Debouncing is really difficult, etc. It will become a nightmare at the end. Next thing of consideration is, wait a minute, paper. Next thing of consideration is the debouncing. The keys are not optimal. They have contacts which do not make the contact immediately. They are bouncing like tennis balls, and contact, no contact, contact, no contact. And this is happening in a frequency anywhere from 100 Hertz to a few kilohertz, depending on the size of your switch and the mechanics there. The presentation you just looked is one way to deal with this kind of debouncing effect. It's called debouncing. The neat thing, when done properly, it also makes the system interference tolerant. Well, when you have decided whether it's an up key or down key event, then just store it. You cannot use it immediately because you usually want to divide your program in smaller parts. One part is dealing with the switching of output. One part is dealing with another thing, and so on. So you cannot build this program around some keyboard reading routine. Therefore, you need a buffer which can be written and read later. This buffer needs to keep the order of events. Okay. This was a little bit of a chat over keyboard. how to read it, etc. Microcontrollers use timers. A timer is something that you fire, it starts counting, and then after a predefined time, it will do something. Like one not so very nice example of a timer is a bomb. You might have a timer there which fires it up after 20 minutes, for example. Not a very good example. Okay, very good. Another very good example is if you are cooking eggs. You have usually this egg clock. You put 10 minutes into it, and then it's a timer. After 10 minutes, it will start ringing and reminding you that if you cook these eggs anymore, they will be too hard to eat. Okay. In a microcontroller, the timers can also measure the time. They can be used that way. There is a third usage for timers in a microcontroller environment, and that is generating waveforms. In this application, we are using the waveform generating property, and we are using the timing property. Okay. The timers in a microcontroller are quite accurate. In our example, this ATmega32, the timers are operating at maximal 8 megahertz. This makes the accuracy about 1 microsecond. Oh, wait a minute. Yeah, 1 microsecond. This is more than enough. Okay, and I mean the resolution. Accuracy is fully dependent on your accuracy of your crystals and the clock and etc. But the resolution is 1 microsecond. Now, this kind of accuracy is very seldomly needed. Furthermore, these microcontrollers, the smaller ones, usually don't contain that many timers. This ATmega32 contains 3 timers, one of which is dedicated to our waveform generation, and then we have only 2 timers to be used. That's not enough. Usually you need at least, well, let's say 5. That's a very reasonable count, and therefore we make a routine which is using 1 timer, but it will run in software, let's say 20 timers. Well, the accuracy cannot be 1 microsecond. It cannot. So 1 millisecond is quite good, and it's more than acceptable on most applications. So we use that kind of timer. There will be a more detailed programming section in this series, and I will go back to that. But the pure hardware timers are really seldomly needed. The accuracy is seldomly needed, and therefore it's better than to use this kind of approach where you have, let's say, 20 timers already available, very easy to use, etc. Okay. Well, that's about the timers. Well, I promised to talk about ring buffers. Ring buffer? No, you don't put your wedding ring in a buffer. No, no, no. A ring buffer is a buffer which is reusing the buffer space. It's circulating the buffer space, and therefore it's named a ring buffer. The features of a ring buffer are that it can be sized according to needs. For example, in our case, we are using a ring buffer for storing the key events. Ring buffer returns the things you enter into it in exactly the same order than you entered them. So it doesn't alter the order of events. That's one thing. Another thing is that when ring buffer becomes full, you can do two things with it. You can accept that it became full, overwrite some data, and well, this results usually in reading garbage. Another way to do this is to do some functionality in the buffer so that it will wait until there is some free space in the buffer. This is a very bad practice. If your program cannot consume the data that is going into the buffer, you cannot cope with that kind of situation. The only way to do that is to enhance the program in a way that it really can handle the data. Yes, there will sometimes be more than one element in the buffer, but usually it should be quite empty. Well, that's about the ring buffer. It contains something like memory space. Suitable sizes for a microcontroller environment are, how come? They are like 4 bytes, 8 bytes, 16 bytes, 32 bytes, and so on. Well, actually it's not bytes. In a ring buffer you can store objects. This means that in our case we store key events. Well, as it happens, a key event is 1 byte wide in my case. And I already decided that the buffer size will be 8 bytes. That should be more than enough to store all buffer the key events. You probably cannot be pushing that fast your keyboard. And there is, of course, this debouncing effect which will further limit the frequency. Yes, it contains this memory space, which is, the suitable sizes are potencies of 2. And then it contains 2 pointers. One is telling where in the memory space you write the byte. And when you have written your byte, it will advance to the next position. And if this position is past the buffer length, then it will go directly to the beginning of the buffer. There is some data in the buffer when the other pointer, the read pointer, is different from the write pointer. So, if the pointers are different, you take the read pointer, read the byte or the item that is pointed by in the buffer, advance to the next, this read pointer, advance it 1 to the next, and if it goes past the buffer put it pointing to the buffer start. They behave identically. The only thing is that when you are writing, you write first and then you advance. And by reading, you read first and then you advance. Well, they behave the same. The other one is used for reading, the other one is used for writing. And there you go. There you have your ring buffer. It's very easy to code. It's it's a good proof of concept. It has been used widely in microcontroller programming. Well, that was all about ring buffers. Well, this was all for today. Next time we go on with some analog to digital things. But this time, have a nice week. See you!